Hello everyone, and thank you for tuning in once again to the Group Theory Podcast. This is the show where we talk to working mathematicians about what it's like to do research for a living. My name is Logan, and today we're joined by Dr. Anne Broadbent, professor here at the University of Ottawa. Dr. Broadbent has won numerous awards, including the Eisenstadt Prize in 2016. Did I pronounce that right? Okay. Yes. For her work in quantum cryptography. And after obtaining her PhD from the University of Montreal in 2008, she began work at Waterloo's Institute for Quantum Computing before taking up a position here at the University of Ottawa. And since obtaining her PhD, Dr. Broadbent has published a whopping 40 articles. So without further ado, thank you very much for joining me today.
Thanks, it's a pleasure to be here.
Okay, so I guess we'll just jump right in. What's your field of research, and how would you describe it to a non-math person?
I work in an area called quantum cryptography, and this is how to update our information infrastructure in terms of security in the advent of quantum information. In particular, I look at protocols. For instance, how could we delegate quantum computations given a powerful quantum server and a conventional computer trying to perform some private computations on that server. Other things related to secure communications using quantum information, and other types of primitives that you would want to do in a quantum world. So I should say quantum information refers to using the properties of quantum physics in order to encode and process information.
Okay. So then, is there any really key differences between quantum cryptography and I don't know what you'd call traditional cryptography? Because I've done a little bit with RSA schemes and
there's something called, I guess you could call it conventional cryptography. People in quantum computing call it classical cryptography, but that can be confused with other things. One of the differences is that we know that quantum computers can perform some computations faster than conventional computers, and one of those computations that they can perform faster is factoring. So a lot of the cryptography that you might learn, for instance, in an undergraduate course, is related to the difficulty of factoring, for instance, RSA. So we need to find alternatives to that. So RSA is not really considered part of quantum cryptography.
Okay. And so what's the kind of math that you actually use? Because I know physics and math have kind of had relationships on and off all throughout history, and recently with L functions, physics has come back into the picture in studying them with random matrices. So is there a similar relationship between the math side and the physics side, or do you mostly deal with physics?
Yeah, good question. And the answer, if you ask different people, you'll get different answers of what type of mathematics or physics do they use. And for me, I use the basic axioms of quantum mechanics to understand how information can be processed and used, and then various theorems that derive from I should call them postulates of quantum mechanics. And then there's a wide variety of mathematical techniques that can be applicable. My own training was in combinatorics and optimization, so sometimes I go more towards graph theory, coding theory.
Okay.
Yeah.
And so you mentioned these postulates of quantum mechanics. Can you just talk briefly about them for some of the viewers who may not be familiar with it, myself included?
Okay. Yeah, the postulates of quantum mechanics tell us what are the evolutions of quantum systems. So, for instance, it's possible to initialize a quantum system to a starting state, and then it's possible to apply what are called unitary transformations. These you can get from your linear algebra course that tells you what are the valid operations that you can apply to quantum states. And then what happens when you measure a quantum system. So then you'll observe a classical message, and this is the way to extract information out of a quantum system. So then there's a rule that says what are the outcomes that are achievable given a possible underlying quantum state. Yeah, so simple postulates, but then they lead to all sorts of interesting phenomena.
Okay. So would you say it'd be like a fair comparison to say then that in math you use the ZFC axioms, and then from those axioms you develop theorems, and then in your work you take these postulates of quantum mechanics and then build theorems as if they were your axioms?
Yeah, but my work is not so much about building theorems than about building protocols. So because it's maybe more applied than some areas of mathematics, I'm looking at ways to do quantum cryptography protocols. So there's, yes, you use the theorems as intermediate steps, but the main goal is to give a protocol and a security proof.
Mm-hmm. So I've done, I don't know if it's changed in the years since I've read this article a couple years back, but we have quantum computers now, but we don't really know how to use them to their fullest extent, right? So how do you even begin to I don't know, code something like that?
Right now, the work that I'm doing is very theoretical, although sometimes I do interact with physicists who have labs and are able to actually build some of these protocols. Quantum computers, I'd say we don't have them right now. We're at the stage where we have a few qubits. Qubits are the basic unit of information. Conventional computation uses the bit, and the quantum computation uses the qubit. So the quantum computers are more of a theoretical tool right now, so you can work on algorithms and protocols just like you would work on conventional algorithms and protocols on paper.
Okay. So, in your professional opinion then, how long until I have my own personal quantum computer in my home?
I think the first need will be to have a cloud quantum computer, so they might have a few worldwide and you can access them remotely. And predictions on the timeline for that, actually there is one right now. It's called the IBM Quantum Experience, but it's just a few qubits. And then now it's a question of scaling that up to more qubits and having them more reliable.
Okay. So what can you do with a few qubits then?
That's one of the questions. That's one of the current areas of research, would be to find applications for short to medium term noisy quantum computations. What can you do that would be useful, that would be better than what you could do with conventional clusters, like large computing centers? Yeah, that's still ongoing research, really.
Okay, yeah, so because from my understanding of how it works, which is very limited, but a qubit, or a regular bit to start, can be like a 1 or a 0, on or off. And then a qubit uses quantum superpositions, and you don't really know what it is, but it could be in between 1 and 0. So how exactly do you manipulate those things, and how do you get any kind of information out of it if it's this nebulous idea of anything between 0 and 1?
Yeah, that nebulous idea, they're called probability amplitudes. So you might think of a random variable as being the closest approximation to something that you may have studied. But here the probability amplitudes are complex numbers, and the square of their the sum of the squares of their moduli is equal to 1. So you can see where you can get a probability distribution out of the probability amplitudes. And so a qubit is a two-dimensional complex vector, and the operations that we can apply to it are unitaries. So, which will modify the probability amplitudes based on the unitary that you're applying. And then when you measure a qubit, you'll observe one of the two bits, 0 or 1, depending on the amplitudes of each of the entries in the complex vector.
Okay. So, is there a way then to so you mentioned that by applying these unitary transformations, we're able to adjust the probabilities. Could you talk a little bit more about how exactly that works, or is that maybe too high level?
Those details don't really give you an intuition of why quantum computing is better, except maybe that the probability amplitudes, as I said, were complex. So you have this interference that you don't have with conventional random variables. And yeah, it turns out that if you're able to strategically work on your unitaries that you're going to apply, you can get some of these interference effects that will amplify a solution that you're looking for better than what you could do with conventional computers.
So now, of the 40 publications that you have already, I mean, quantum physics in particular is known as being this thing that's got all these sorts of surprising results, like the double slit experiment or quantum tunneling, quantum entanglement. But is there anything that personally surprised you in your career so far?
Excuse me. One of the first quantum phenomena that surprised me and on which I worked a little bit was quantum entanglement and one of its embodiments, which is what's called quantum pseudo-telepathy. So this is a situation where parties can, let's say Alice and Bob, they are able to, they play a game against, it's a cooperative game, against a referee. And using entanglement, they're able to produce correlations that the referee will observe that are not available to them if they had only conventional or classical resources. So it's a situation where you're very surprised because when you see what the correlations that they can perform, and you realize that they can't do this with conventional information, that I think it shows you one of the powers of quantum information.
Okay, I was actually going to ask you about pseudo-telepathy because I was looking through some of your publications and I thought, wow, that's a really cool word. So, in my understanding, quantum entanglement, you can't like transmit information by doing it though, right? Because that would violate relativity. So how is it that using quantum entanglement, you can somehow have more information than before?
Well, it's not that Alice and Bob gain any information about what the other party has on their side. It's more about correlations, and this you don't need to understand quantum mechanics to understand that correlations do not necessarily involve communication. Like you could, there's this thought experiment or thinking about an abstract device that takes as input from Alice a bit and from input from Bob another bit. So say A for Alice and B for Bob as inputs. And this hypothetical device, it's called a non-local box. It then outputs a bit X to Alice and a bit Y to Bob, such that the parity of the output is equal to the product of the inputs. And this device does not imply communication, because actually locally each party will see a random bit as the output. Locally it's random, but there's correlations between the outcomes of this box that actually neither classical theory nor quantum mechanics is able to emulate perfectly this box, but quantum theory is able to emulate it better than classical theory, so probability close to 85%, whereas classically you can do this with probability close to equal to 75%.
Okay, so is there some even better theory out there than quantum mechanics that would be able to emulate it perfectly?
That's the question, and some of my work relates to saying why such a theory does not exist. So we could postulate such a theory, and then we actually arrive to some funny consequences related to information processing. Actually, something called communication complexity that tells us that intrinsically there are some functions that are difficult to compute, and when you have a cost related to communication between Alice and Bob. And with this hypothetical device, the non-local box, then you're actually able to trivialize all of communication complexity. And this sounds like this should not be possible in nature. So we're actually at the point of thinking of why there should be rules on our physical reality based on information processing principles.
Okay, that's interesting. So then I guess we'll just move along then a little bit here. So when did you decide that math was kind of the career path that you wanted to follow?
I would say there's not exactly a point in time that I decided that it was a career path. There was the big decision of what do I want to study as an undergraduate degree, and I had lots of various interests. But I'm very happy that I focused on mathematics. And then I enjoyed mathematics a lot, and one thing led to another. I ended up doing a master's and then ended up doing a PhD. I always had this backup plan of doing cryptography, which is related to mathematics, which is one of the reasons that maybe my research choices were focused on cryptography, but I also find it really interesting, of course. And then, one thing led to another, a postdoc and a tenure track position.
It's funny you say that, because almost all the professors we've interviewed, when we ask them that question, they have the same answer. It's just, well, I just kind of ended up here. I didn't really plan for it.
It was not an easy path, though.
No, of course not. It's a math PhD. So I guess then, during your undergrad, you focused on the math, but then what led you to quantum cryptography in particular? Was there like a specific course you took, or?
I guess it was a combination of quantum and cryptography, and I only got into quantum cryptography towards the end of my grad studies. I went to University of Montreal for grad school for my master's initially, not necessarily with the intention of doing quantum computing, but with the intention of doing cryptography. But I ended up working on some problems that were related to quantum pseudo-telepathy at first, and then eventually quantum cryptography.
Okay. So then moving on, after you finished your PhD, you worked with the IQC, and then now you're doing a professorship here. So I'm wondering, what are some of the similarities and differences between working with like the IQC, where you're doing like, I don't really know how it works. It's like the only security guarded building on campus. But working there and working here, what are some of the similarities and differences?
Well, the big difference is that I had a different position. So at the IQC, I was there as a postdoc, and then that's a time to really add breadth and depth to one's research portfolio and expertise. So I was focusing on developing my own identity as a researcher, focusing on solving some problems that I found really interesting, and forging collaborations, meeting a lot of people. So there were lots of seminars, lots of opportunities to collaborate and discuss. And then the natural next step is, I was fortunate to get a position here, and now my responsibilities are quite different, where I have my own research group, grad students, lecturing, applying for grants, and all sorts of other administrative things.
Okay. Now, what was the first original mathematical result you remember producing, even if it wasn't something publishable?
Well, if you don't mind, I'll take that question a little bit from a different angle. I wanted to tell you a story of something that happened in grade 9.
Okay.
So in grade 9, I don't think you're going to find some new original mathematical results, but originality is sometimes in the eye of the beholder.
Yeah.
So in grade 9, what happened is that I had a math teacher that challenged us to derive our own mathematical theorems, if I could call them theorems. And the example that I still remember was that we were studying triangular numbers. So this is things like, you want to study the sum 1 plus 2 plus 3 up to n. And via some exploratory process, the challenge was to find a formula for that. And only 2 students in that class figured out a formula. So I shared the glory with another student in my class to say, okay, we figured this out. And that's, I guess, when I realized that math is a living science, and it's possible to contribute it, or to have our own individual contributions to mathematics. Because since before then, it was more like I will learn from a textbook something that somebody else already invented. But then I realized that it's possible to find new interpretations, results. So that was my little story of first time I realized that I could maybe find something interesting in mathematics.
Do you remember how you did it? Was this the same way as Gauss in like the story?
I think we were very free in what approach we wanted to do, but there were some suggestions of a geometric approach. Like for me, what worked was to kind of draw a picture of a triangle of these numbers and then complete the square, and then that I knew how to multiply n times n plus 1 to get the sum of the entire square, and then needed to divide by 2 to cancel out the terms that were doubled.
It's really creative. It sounds like you had a good grade 9 math teacher.
Yes.
So would you say like grade 9 then was kind of where your interest in math really sparked, or was it even before that?
I think I always liked math, but I denied it a lot. It wasn't very cool.
It's a real shame because it is a cool subject.
Mm-hmm.
Okay, so what would you say is your most proud mathematical achievement so far?
About 10 years ago, I developed with 2 collaborators something that's called blind quantum computing. And going along the lines of a protocol, this is a new protocol, a new way to do something. Actually, not just a new way to do something, but a new thing that you might want to do. Like, nobody had ever conceptualized that you might want to delegate computations in the way that we did it. So it's a way for, I already alluded to this briefly before, a way to execute a quantum computation in a quantum cloud, but while maintaining privacy. And actually the privacy here will be perfect. So you can imagine that Alice has a computation that she wants to perform. She doesn't have the power to do it. It's a quantum computation. And here with some interaction, they're able to delegate the computation to the cloud, and her computation itself and her input will remain perfectly private.
That's awesome. So what's the process of coming up with something like that? Because that's kind of like an invention in a sense of this new way of doing something.
Mm-hmm. I really like the collaboration aspect of it. All 3 of us were working on some areas that were related but not identical, and I don't think that we could have individually come up with this, but it was my collaborator Joseph Fitzsimons. He had this perspective of how we could possibly add randomness to a quantum computation, and then me from my cryptographic perspective, I realized, well, we could use this to delegate a computation. And then there was also another collaborator, Elham Kashefi, who's working in a measure-based model for quantum computation, which ended up being the model in which we were able to get this intuition, and she was also able to formalize how we could do this blind version of computation.
That's really cool. Yeah, I love how collaborative math is. A lot of people think it's just a bunch of lonely nerds sitting in their office all day, but it really is something where you got to go out, you got to meet people, and you got to discuss your ideas. And I think that's a part of what makes it such a wonderful subject.
Yeah.
Okay, so the flip side then to proudest mathematical achievement is, what's the one problem you haven't been able to solve yet but wish you could?
I think that there's no one problem. I think I'll be most happy when I find a new paradigm. Again, like really, there's some areas that I think there's some interesting questions to look at, but I actually don't know the question yet. So I'd like to understand more about quantum unclonability, for instance, which is related to it's not possible to copy quantum information perfectly, and this seems to have a lot of consequences that we know about, but I don't think we quite understand yet if there's some underlying information principle that can be used in cryptography the way that we usually have these principles in cryptography. It's one thing I'd like to understand, but I don't know if that's going to be the ultimate question, or there might be something else.
Okay. Yeah, because so in some of the other professors I've talked to, they say they're kind of like, there's like 2 camps of mathematicians. There's the ones that kind of like to sit on one problem and just try and solve something, and then there's the other camp where they're kind of more exploratory in that they want to know, okay, well, how do we not like build something instead of solve a problem? They want to build a new area of math in a sense. So would you put yourself in that camp?
Yeah, definitely. I put myself in that camp. I think that that's one of my strengths is creativity, and I think that's where I can be most productive in coming up with new avenues and new problems to solve. I don't really like to sit on a single problem. I have a bunch on the back burner trying to look for techniques, and maybe it's someday I find a technique and then can apply it. I kind of compare my problem solving process to solving a jigsaw puzzle. So there's a bunch of pieces, theorems, proofs, etc. I put them together. I try to put them together to maybe solve the problem, the picture that's on the box, which is my initial goal. But often the initial goal either becomes unattainable, and then I realize why, or I find some other goal that's even better, and then so my picture ends up being completely different. And that's actually one of the fun parts.
Okay, so how would you describe then, so that's your problem-solving approach, how would you describe your research approach in general? What does a day in the life of you doing research look like?
I wish I could do more of these research days. Right now I work a lot with the students that I have, and the postdocs and collaborators, and there's a variety of stages of the research, of coming up with initial ideas or problems to solve, of looking at the literature for techniques that would be applicable, of writing the actual paper. No day is identical.
Okay, fair enough. So do you have a favorite theorem?
Favorite theorem, very simple theorem, very simple proof, but very profound. No cloning theorem, quantum no cloning theorem, which I alluded to earlier on. Tells us that it's not possible in general to copy arbitrary quantum state.
Okay. Is there could you talk a little bit more about why that is, or is that too high level?
It's a consequence of the formalism and of the linear algebra that underlies the quantum theory. And the proof is a contradiction. It says, well, if you tried to copy, if you had some sort of hypothetical copying device, or cloning device as they're called, then you can really quickly lead to some contradiction. Contradicts the linearity of quantum mechanics.
It's a tough word. Okay, well, that's really cool. Got any math jokes?
Oh, they're cheesy. So, I'm sure you've heard this one before. I like it. I don't know. Complex analysis is all fun and games until somebody loses an eye.
I could see the shame. Yeah, math jokes. Mathematicians are not known as comedians for a reason, I think. But
I like the prof quotes in the math news. Is that still around?
Yeah, it is. Yeah, there's a couple good ones, a couple good nuggets.
Yeah, I was pretty proud of being quoted once or twice in there when I was lecturing a few years ago.
Oh yeah?
Yes.
Oh,
I actually made an effort to be in there.
To be in there, yeah. So do you like recreational math? Do you find yourself just doing math all the time? Like, do you have a favorite like mathematical game to play with yourself?
No.
No? Okay, fair enough. I mean, you got to balance your life, right? If it's
I
all
use my
math.
brain cycles towards other stuff.
Of course, for sure. Do you have any mathematical heroes?
The one that comes to mind is Bill Tutt. Bill Tutt was a British-trained mathematician. He played a very important role in the World War II efforts by the Allies for code breaking in Bletchley Park, UK. And all of this, his World War II efforts were only known a decade or two ago because it was highly classified. After the war, he obtained a PhD in graph theory, and then shortly after that, he moved to Canada, first to Toronto, and then had a long and productive career at the University of Waterloo in the Department of Common Torques and Optimization.
Mm-hmm. He's got a big poster on the wall in the MC building.
Oh, good.
Yeah, and they talk about him all the time at like the orientations and stuff. He's a very influential figure.
Yes, in many areas that he worked on in graph theory, knot theory, and also his code breaking efforts were very important.
Do you have a favorite story from math history?
No, nothing comes to mind.
Okay, fair enough. Okay, so we're almost through all the questions now. But I did want to know, because like quantum mechanics is like the cutting edge of research right now in a lot of different fields. Are there any huge breakthroughs that have recently come through?
In the last 18 months, a lot has changed in quantum computing because we're now seeing many companies, big companies that have a important effort in building quantum computers, and that changes the game where we have the impression that this quantum computer might actually arrive soon. I know it's not a breakthrough in itself, but it's leading up to a potential breakthrough. There was a breakthrough recently, also experimental, that was about that pseudo-telepathy game that I talked to you about. There's a variant of that was actually demonstrated, and then so that it was clear from all points of view, no matter how kind of paranoid you might be about how the experiment was set up, that the quantum mechanics does have that advantage in terms of the correlations. So that also means that we can continue with our theory work. It seems like it's really on solid ground. So we can continue to study entanglement. The area that I'm interested in delegating, quantum computations, has had some recent theoretical breakthroughs. Something called quantum homomorphic encryption. So that's a way to allow a remote server to perform computations on encrypted data related to the scenario that I've mentioned to before, but non-interactive. And there's been some results recently on how to do that for quantum computations. So we're seeing that also quantum cryptography is now kind of catching up a bit to conventional cryptography, and we're able to have protocols and proofs that are closer to what we understand for the classical or conventional world. So I think there's still going to be lots of interesting results coming up.
Okay. And actually that brings up another question that I had. So going back to conventional cryptography and things like RSA schemes, which really kind of, I guess, fundamentally rely on the computational complexity of factoring big numbers. So does quantum cryptography work in a similar way, where it's not necessarily factoring big numbers, but does it rely on computational complexity to protect the data, or does it work in another way? I know from what little I've read, that if someone tries to observe a message sent through a quantum computer, like the wave will collapse and then the information is lost. So but that's not related to the computational complexity. That's just
yes, exactly. That's a physical principle. And indeed, quantum cryptography is in a wide area, but it's mostly well known for quantum key distribution, which is a way to communicate securely. And the big advantage here is that we're able to base security proofs on the physical principles of quantum mechanics and not on any computational or complexity theory assumption.
Okay. So then, I mean, with RSA schemes, if you just happen to get lucky, which I mean, 0.0000001% that you end up guessing the 2 prime factors, or the n prime factors, or whatever it is, but you could still crack it. So can you crack quantum cryptography, or is it more foolproof because it's reliant on these fundamental properties of nature?
The idea of guessing the key and being lucky, there's ways around that. So there could be ways to encode the data so that guessing a key gives you no advantage actually on seeing that your guess was correct. And that could be something that can be also used in quantum cryptography. So you have the same probability of guessing correctly than in conventional cryptography. But that's not usually the figure of comparison or the figure of merit that you look at for breaking the scheme.
Okay, so what would you look at then?
you look at some advantage in some hypothetical game. So where the attacker is given a ciphertext and needs to distinguish that ciphertext from a random ciphertext, let's say. And so there always is that probability, yes, of guessing correctly. But in the conventional world, we're only able to show these kind of security games and bound the probability based on some underlying assumption. And it turns out for the quantum cryptography, you don't need to make that assumption.
Okay, really cool. Okay, so I've got one last question for you, and that's what advice could you give to us aspiring mathematicians?
So, I think mathematics is super interesting, but everybody has their own approach to it, and everybody has their own strengths. And I think that one of the keys is to figure out what are your strengths, what are your interests, and then go with that. And that's how you'll be able to have the most impact, and also keep up your motivation and interest, and just in general feel more accomplished. That'll give you your own mathematical identity, and have confidence in that identity that you have your own space in which you can contribute. Try not to compare yourself to others, because that can be detrimental to your self-esteem. Just keep on going, believe in yourself, and enjoy.
Okay, well, thank you very much. Okay, well, thank you very much for coming on the show.
Thank you.
All right, bye-bye.